let's see. I put up homework 1 this morning, so it is now available. Because of the timing with trying to fight through the virtual desktop, I decided to bump it back 2 days. So it was originally due on the 10th, which was a Monday night in week 4. Note that I changed the dates to be Tuesday, Wednesday, Thursday on week 4 on this calendar, so it's due Wednesday night. So I always want to make sure that you have a full week after we cover something before your homework is due on it. I guarantee that getting the virtual desktop thing to work will be the hardest part of this assignment. That is really what it's for, is just to give you practice getting into the system, because that part takes the longest. The rest of it is just going to be generating the types of univariate statistics that we've been talking about. The write-up for it is going to look like a method section. So these are the types of things that you would know how to do at this point. So that's what we're going to get some practice with. So we have a little bit left of lecture 1 to do today, and then we can fight with your software. Yay! Yeah, I know. I wish there were an easier way, but at least you don't have to pay, right? Like that's the thing. Learning how to navigate networks and things like that is a valuable skill, even without the context of statistics. So hopefully this will not be for naught, but we were talking about stats last time, right? Mm-hmm. Let's do some reviewing. What do you remember from last time? I'll give you a moment to collect your thoughts. I will take letters, phrases, gestures, questions. Skew. Skewness. Skew or skewness. And what comes to mind? Positively and negatively. And how do you know which is which? Which label goes with which?
They're opposite.
They're opposite. Positive and negative are opposite. But it's where the tail is. So let me pull up some pictures for reference here. Let's see. Like that one. This is slide 13. So negatively skewed is the left one because the tail is heading towards the negative side, even though it's not actually a negative number, but it's the direction. It's heading that way. And then positive on those. Synonyms for skewness? Feel free to read from the slide. This is just a review.
Asymmetric.
Yeah, asymmetry of some kind. My other one, I like to make up words, shoved overness of the distribution. Why does it matter if something's skewed? Because it affects what?
The mean, median, and mode.
Mean, median, and mode. Let's look at that picture.
Those are central tendencies.
Oh, yes, they are. They are central tendencies, meaning ways of indexing what a middle value is. So how do you calculate those 3 things?
Same way we did it in elementary school.
Yes! It hasn't changed. The mean is the mean, although there are other kinds. We're talking about the arithmetic mean. How do you find a median? I'll accept 2 different answers. What's the hard way? Well, I guess hard is subjective.
Add it up and divide it up.
Line them all up.
Line them all up. Yeah, add it up and divide by n is the mean. The median is the middle value. So you literally have to arrange them and then find the middle. That's the hard way. The easy way, ask for it in software.
Oh. Let's do it that way.
Let's do it that way. Correct. Yes. Likewise, how do you find a mode? It's the most frequent. Yep. Again, sort it, look manually, or ask the software. Sorting it and looking manually will start to be impossible with sufficiently large data sets without error. So yes, ask the software will be a refrain because that's how things are done in the real world. So when we have skewed data, these 3 measures of middle disagree. So then it would matter what you report. What is the thing you are going to see most often by far in the context of building models to answer research questions? Which of these 3? What are the models going to be focusing on capturing? The mode, the median, or the mean? It's the mean, yeah. So you learn this in terms of describing data, but then it goes away. right away. There are actually models that work with the median. It's something called quantile regression instead, and I'm hopefully going to get a chance to teach that in my other class, the one that meets after this one. But the mean is really the ruler of the world for all intents and purposes. So, okay, skewness, people remember. What else do you remember? What other things besides middle and asymmetry do we need to know to describe a variable that's quantitative?
Variance.
Variance, yeah, what's variance? I'll take a conceptual definition or the formula, your choice.
Being far away from the moon.
Being far away, yes, this is where the gestures come in. Yes, I accept gestures. Yeah, this is variance, like little variance, big variance, yes.
Kurtosis goes with that then too, right?
Kurtosis is like squishiness. Yeah, it's like it's shoved in the middle and not like it's related to variance. It's really hard to tell them apart. And kurtosis is not a thing. Like it stops being a thing that people pay attention to real quick. Just telling you. Yeah, so how do we find variance?
Average squared deviation.
Average squared deviation. Yeah, that's the definition. So we take each person's value, subtract the mean, square it. So order of operations matters, right? So it's subtract, then square. Now why do we square? So it stays positive. So the negatives and positives don't cancel each other out. So it's kind of like absolute value in terms of what it's for, although that's a different operation. So we square the deviations for each person, then do what? Add them up. And the Greek letter that goes with add them up?
Sigma.
Little or big?
Big.
Big one, yes. Yes, gestures, although mine's backwards, no. But yeah. Yep. Then what do we do with it? You subtract it, square it, sum it. One more thing.
Divide it?
Divide it by
N? Minus 1?
N or N minus 1.
Yes, one of those.
You'll see different. You'll see different versions of the formula. N minus 1 is the one that's unbiased. Why is it minus 1?
Because we're...
Related to degrees of freedom?
Yes, it is. So that quantity, that N minus 1, is what's known as denominator degrees of freedom, meaning it's on the bottom. Sorry, I'm taking my boots off as we do this here. You're welcome to remove your shoes too. I'm still not used to showing up to work in like dress clothes and dress shoes. My calves are really not happy with this decision to wear boots, but they're the things that keep me out of the snowbanks. Anywho, yes, degrees of freedom, the concept. So this will show up again and again and again. It's the idea that you have as many chances to capture the information in a variable as you have people, because that's how the variable is made. So we spent one chance. We spent 1 point, so to speak, to calculate the mean, to calculate the variance. So that's down by 1. Later on, when we calculate something called residual variance, which is variance left over, variance that's unexplained, we will want to know how many things did we have to calculate to try and explain any part of it. And so we will ding ourselves for those things, for slopes in that case. So yeah, it starts with N minus 1. What's other word you know relates to variance? Standard deviation, how does it relate? More question.
Square root of the variance.
Square root of the variance, yes. So it's the average deviation. You can think of it as an unsigned number. Yep. What other vocabulary do we have? Anything else you can think of? How about notation? So think of, you referred to elementary school a few minutes ago. Think about like flashcards, right? Do kids still do flashcards? Or is there like an app where you hit a button and a card pops up and then it disappears?
More of an app.
There's an app, okay, yeah. But the flashcard concept, right? Because what makes statistics hard is not the math. We're going to have the software do the math. That's not a problem. What makes it hard is the working memory load that goes into managing this. There's words, there's formulas, there's symbols in the formulas, and if you don't speak the language fluently, it gets really hard to keep track of what's going on. So drilling notation is going to be just as important as drilling vocabulary. So what kind of notation shows up when you are calculating a mean?
Mu.
mu, that's supposed to be for what the population mean is. That's the U looking thing, Greek letter. What other notation? How about for population standard deviation? Yeah, gestures. What's it called? It's little sigma, yeah.
Sigma.
Yeah, and I don't know who decided this, but like the world agrees that this is what it's called. How about population variance? So if population standard deviation is sigma, population variance is. Yeah, I'm seeing everyone's making the gestures. Yes, sigma squared. Do you remember how to make a sigma squared? Like in Word?
Yeah.
Yeah.
Um,
So there's two ways.
equals.
Yeah, the hard way, the Hunt and Peck version of equations. If you go up to the insert menu, there's symbols. And then there's more symbols. And then you can scroll for a few days for all of these characters until you eventually find the Greek letters and Hunt and Peck. Or you can do what? How do I start?
S caret 2 or sigma caret 2.
But how do I get it to understand that's what I'm doing?
Alt
Yeah,
equals.
alt equal, yeah, or insert equation, that's the keyboard shortcut. And so then if I want to do, let's say sigma squared, slash, the one that's above the enter, the word sigma, and then what do I do to make it jump? Yeah, spacebar will do it, enter will exit the equation and make it jump. But I'm not done yet. I want a square term that's a superscript. Superscript it, like that. Okay,
Hat.
yeah, hats are another story. I actually don't know how to make hats without the Hunt and Peck method. But once you're inside the equation, there's a new menu that pops up, and there is an accent, and you can do hats and bars and dots and all kinds of stuff over here.
There's a third way.
What's the third way?
If your screen is touchscreen,
Mm-hmm.
you can use and word the ink equation.
If your screen is touchscreen, you can do what? I'm sorry?
Ink equation.
Ink equation?
And then you just draw it.
Oh, that would be nice. Okay, yeah, I don't have that kind of technology. I have the old-fashioned sort of laptop here, but yeah, someday. Aspirations. Thank you for that. I didn't know that. So if this is the population variance, right, we all agree on that?
Mhm.
That sounds familiar? Do I need an I on it? A subscript I like that? What do you think?
Isn't it implied because it's a variant, so it would be all the individual scores?
It's the variance across individuals. But what does it mean in terms of notation if I put an I on something versus if I don't? This is one of the vocabulary words from last week. Which letters get I's and which ones don't? Let's look back here and review. Yeah, individual. So things that vary across individuals get I's, otherwise known as, starts with a V. Starts with a V. The idea that something varies across the cases in your data set. Yeah, vary. Yeah, it's a variable. Exactly. I gave it away. My bad. Here we go. This is the slide I'm on, slide 14. So you're going to start to see this kind of notation very frequently. Within a few weeks, we'll be writing equations that describe how predictors relate to outcomes, and this is the kind of language that we'll use to talk about it. Anything that has an I subscript varies across cases, individuals. Anything that does not is constant across cases. So the answer up to this point, variance, whether this is the sample version or population version, there's one variance that describes everybody, it's a constant. If you were to allow different kinds of people to have different amounts of variance, then you get a variable, then you get a subscript. But that's not happening in this class. It does happen eventually. But. But yeah, so when we look at these things, things that do not have I subscripts are constants that describe everybody. Things that do are variables. Let's see. Anything else I'm forgetting? Besides variance, what's another way you can talk about like dispersion? Like a way that might be preferable if your variable is not symmetric and it's kind of screwy looking.
Interquartiles.
Interquartile range. Yeah, IQR is how that's abbreviated. That's the difference between the 25th percentile and the 75th percentile. And the 50th percentile, by the way, has a special term for it. 50th percentile is a special name. I'd say it starts with an M, but that's not going to help much. Not the mean. Related, though. Very close. Not the mode. Other one.
Median.
Median. Yeah, the middleist value is the 50th percentile. Homework question. All right. Anything else I'm forgetting? All right. So when we introduce these things like variance, we make a distinction about S versus sigma. That's going to go away real quick. When you start talking about models, it's going to switch to sigma because we know that we only have one sample and that we're trying to make an inference about the population. It's just sort of a given. So people start talking in population notation. All right. So we were started at the end here talking about sampling distributions of statistics. And my way of explaining that, starting on slide 21 here, is it's the idea of like, okay, this is the mean. How confident am I that this is really the mean? Meaning that my sample mean is a good approximation of the population mean. It's the mean, or is it the mean? Yeah. Mean, period, or mean question mark. So I didn't do my thing. I was born in St. Joe, Missouri, but spent most of my life within about a 3-hour radius of Omaha. I moved around a lot, but within all like the 4 quadrants. And where I'm from, there is a religion known as 10-point pitch that shows up on Thanksgiving and holidays. Do you guys know this card game? It must be a Nebraska thing. No, it's like a way of life. There's also variance that's 5-point, 10-point, 13-point, but one of the things, like in hearts, it requires you to make a bid at the beginning as to how many points you think you can capture. And there's sort of an ongoing joke that certain members of my family, myself included, are risk averse, and others are much less so. So whenever I make a bid, it usually has a question mark, like 4, like I think maybe 4, as opposed to 6, like I've got this. Right, that's the question we're answering. Like, how certain are we that this is the thing that we can trust? And we're talking about this for the mean, but the same concept shows up in any other summary of your data that you're going to try to work with. A summary of your sample meaning a statistic. So we're going to rely on asymptotic sampling distributions to be able to quantify this. There are other ways, as I mentioned before. So first question. In a sample, what affects how close the sample mean is, y bar, to the true value of the population mean? And we looked at this and we came up with 2 things. Do you remember? What affects the certainty with which we say, yes, the sample mean is a good approximation of the population mean? How close it is? Sample size. Is more people better or fewer people better? More, yeah. So I had a slide about that. The mean is a little more wiggly. The fewer people you have, wiggly being another technical term. Same thing with variance. The more variance you have around the mean, the harder it is to nail down the mean. So your confidence, I guess, can be expressed in characterizing a sampling distribution of the mean itself. And that is not the same thing as the sample, which is a hard concept sometimes, but this is where we left off with. So if you think about the idea of replicability in research, if you were to select the same kind of sample, the same number of people, the same selection criteria, all of that, and do it over and over and over and over again, the sampling distribution of the mean is trying to characterize how discrepant those individual samples' means would be. Because you know they're not going to come out exactly the same. Right? In theory, if we've done a good job with selecting the right kind of people, we can generalize our sample to the population, but any one sample is not going to give you the exact right answer. They're going to wiggle. So what we hope is that the middle is the right answer, the population mean, but then we need an index of how far off any one sample is expected to be. And that how far off is what's known as standard error. So we will have standard errors of means. You can actually have standard errors of variances. You can have standard errors of intercepts, of slopes, of anything that you calculate about a sample. You want to know how wiggly is it. And in a lot of cases, whether or not it's different than zero if it's a measure of association. That's coming next unit. So the way that you would phrase this is that mu is the mean of the mean distribution, and this thing is the standard deviation of that distribution. But given that standard deviation is in the formula, it gets confusing, and so this is where people call it the standard error instead. And standard error is an index of imprecision. So error means bad, right? So it's backwards. It's like more error, less precision. And you need more people and less variance to have less error. And so trying to understand how this works, then I had an example that I came up with last semester that I'd like to revisit. I got a real can this time, not the baby bottle, although I was amused to see this is 12 ounces as well. The little baby bottles are the same as the cans. I was like, really? Like, that seems like a Piaget conservation of matter thing that I should have already known, but clearly I specialize in things that aren't related to special reasoning. So, thank goodness. So this thing is 12 ounces, and I am dependent on this can to get me through the rest of my afternoon, which is another class, office hours, wrestling my 4-year-old into the car after daycare and negotiating with him about how many carrots he's willing to eat to get dessert. That's the rest of my day in a nutshell. So what if I measured how much liquid is in this can, wanting to make sure that I had everything that was supposed to be, and it actually came out to something different? What if it came out to be 11.7 ounces instead of 12? Ruh-roh, Raggy. Now, is that just a fluke? I don't know. Well, how do I answer that question? Well, I open up every other can in my 12-pack, I measure it carefully, and I try to come up with a sample mean. A pack mean, if you will. Let's say that it works out to be 11.8. Now, is that far enough from 12 to be cause for alarm? I don't know. The other thing I'd want to know is not just what's the mean, but what's the variability around it, right? Because maybe some of the cans have extra. It doesn't go all the way up to the top. There might be room for, like, a little tiny extra piece of an ounce. What if I found out that across my sample, I calculated the standard deviation and it was something like 0.2? We start labeling these things. So we'll say this is the pack mean, this is the pack SD. So on average, this would mean that each can is off from the mean of its pack by 0.2 in either direction, too high or too low. Now, is my pack representative of all packs of soda that are out there? Should I file a lawsuit claiming systematic misappropriation of caffeine? I don't know.
And we need a larger sample size, right?
Well, let's see. And let's say that I am working with a 12-pack. Could happen. Standard error of the mean. I'm going to say it this way because SEM means a whole bunch of different things depending on which class you're in. How do I calculate that? What's on top? I said you don't have to memorize formulas. I'll give it to you. It's standard deviation of my sample divided by square root. Sorry, I said it again. Square root, yep. of this. Okay. All right.
So what's the difference between the capital N and the italics capital N again? Because you said that.
Yep. So in the context, if n is preceded by a squiggle, a tilde, it means normal distribution because the squiggle means is distributed as.
Right.
I'm trying to use italics versus not as a further way to delineate them. That this would be the n, here I'll make it italics, for sample size. So the standard error of the mean in this case is 0.06. Now what does that mean and how is it different than that one? The answer is level of abstraction. The pack standard deviation is how far off each can is on average from the mean from that pack. This number right here, the standard error of the mean, is how far off my pack mean is on average from the population mean.
Do you mind showing the, how you calculated that?
Sure.
I
Yep.
was looking down into this.
So I entered 11.8. I'm just making up numbers off the top of my head, right? Okay. Well, they are relevant because 12 is, my anchor point here, otherwise known as my null hypothesis. That's coming next too. Pack standard deviation, I just pulled this number, 0.2. I'm using a 12 pack. So the standard error of the mean, unfortunately I can't zoom in on the formula very well, but I'll do this. It is the standard deviation for your sample divided by the square root of your sample size.
So you started with the equal sign?
Yes, to do, yeah. So you can make Excel do math by saying equals. Yeah, so if I took off the equal sign, it just thinks I'm typing formulas.
Okay.
Yeah, let me do that. We'll paste that there for reference. Equals beta 2 over square root. There we go. Oh, nope. And that means, hey, you can't do that. Because it's trying to divide by 0. So let me move that down, move that down. There we go. So this number right here, this 0.2 and this 0.06, they're each kinds of offnesses. What they're off from is what's different about them. The 0.2 is how far off any can is from the same pack, from the pack's mean. Then a higher level of abstraction, this 0.06 is how far off that pack's mean is from the mean across all the packs.
How do you know the mean of all packs?
Estimated, right?
You have to believe.
Oh, look, faith.
Faith.
How do you believe?
So
How are
you,
we believing? Like, why not just test a bunch of 12 packs? Where does it come from?
so yes, so that's part of the replication crisis, right? Is that we're taking one sample of data and we're trying to use only that sample's information to make an inference about what would happen across all the packs. Yes, you are correct to give me that face. Like, what? No, it's true. I know, that's what we're doing. Everyone agrees that this is okay, but here's the thing. What if you're skeptical because it's only a 12 pack? What if I did a 24 pack? What's going to happen to my standard error of the mean? Down to 0.04. What if the difference between each can and the average of the cans was smaller? Let's make it 0.1 instead. What's going to happen to the standard error of the mean? Smaller? What if it were 0.3? Bigger. So if you only have, say, 6 cans, right, it's a nonlinear relationship. But the smaller your one sample and the more variance around the mean, the less certain you can be about, basically the more the sample mean is expected to vary around the population mean. But yes, you totally just have to believe that your sample, the population mean, is what you're going after. Now in this case, I know the right answer. This is what's known as a population mean that's known, right? What is this supposed to be? 12. Population mean. I'm going to enter that one here, 12. So what do you think about these two numbers? Is 11.8 close enough to 12 within sort of expected fluctuation, or do you think it's suspicious? Think it's suspicious? Yeah, what if I told you there was a test for that? And that the basis of it is right here. If you know the standard error, you have a significance test that's possible to say whether or not any one sample mean is different than the mean of the population it's supposed to be. If you want to learn how to do that, come back next week. That's in the next lecture. I'm going to leave you hanging. But the thing that I want to try to drive home is that these two offnesses are different numbers. The PAC standard deviation is cans relative to mean of the cans. The standard error of the mean is how the PAC mean differs from the population mean.
Is one of these numbers more important than the other? I understand that you have to have one to calculate the other.
Yeah.
But if I was reading results of somebody's thing, like maybe they only gave me the standard error and not the standard deviation?
So
they gave you the standard error at all?
So that is one thing in terms of results, is that people typically give you either the standard deviation or the standard error. And so it may be up to you to figure out which one that is. Standard deviation is typically abbreviated SD, and standard error is SE, so hopefully they use those labels. But yeah, standard error is nothing more than the combination of standard deviation and sample size. So in terms of which is more important, you'd probably have to do some sort of, like I'm picturing some kind of asymptotic curve, right? As the sample size increases relative to variance, it's the square root of the sample size, so variance probably matters more. But this basic idea that it's variance that you don't know on the top relative to how many people you have to counteract it, that shows up in the formula for standard error for everything else as well. Yeah?
Would it also depend on if you're looking in a class and you're comparing people within the class versus comparing this class to other classes, like PAC?
Yeah, that's one way to yeah, so it's a different, you're trying to make a conclusion about a different source of variability and different reasons for that. So the reasons why any one student would be different from like the class average is a different set of reasons than why the mean of one class would be different from the mean of all the classes. They're both types of variance or dispersion, but they're different in nature. Other thoughts, questions? Okay. So this idea of what happens to the sample mean, there is something that I'm guessing you've heard of, probably not in elementary school, but in previous classes. Have you heard of the central limit theorem? You heard of it, could recite it, or just heard of it? Just heard of it. Is that what I'm hearing? Right, Jeff? Yep, just, okay, here, doing it again. Cheryl, Ming, Jen, Jeff, G/April, Jose stepped out, John Paul, Dre, Alexis, Amanda, Jacob, Ashley, Willie, Carly. Still got it, okay. All right. See, I say it's only fair. If I ask you to drill like notation and vocabulary, I'm gonna drill your names in the same way. But yeah, so it turns out that that sampling distribution of the sample mean itself is always normal, even if the variable that it is the mean for is not. So this is something that I think people sometimes get confused by. This tendency that, again, someone proved a long time ago, so we can just believe it, it's a thing. I'm not going to bore you with the proofs, but that's just the way that we've all taken it to be accepted fact. It's not that all variables, if you have enough people, are eventually normal. That's not it. It's that the sampling distribution of the mean heads towards normal the more people you have. And to demonstrate, I have an example distribution here. This is slide 29, where this is a distribution that's called uniform. You don't see this in real data very often, but it's something that's used in simulated data to make sure that you have values that are equally likely across a range. So a uniform distribution has a minimum at A and a maximum at B, but all values are equally likely between them. So I'm going to demonstrate the central limit theorem by taking the mean of individual values that take that distribution. Now this is a box, right? Like this is one of the definitions of non-normal, right? You don't get much more non-normal than a box. But if I take this box and I draw 30 cases of a variable that follows that box distribution, and I do that 500 times, so I have 500 samples of 30 people each, and I plot the distribution of the mean from each sample, this is what it looks like. It'll look close to this. I mean, it's not exact, but this is something you can demonstrate. If I take 100 cases from the box, I do that 500 times. It gets even more normal in the middle here. 250 from the box, even more normal. So the more cases in an individual sample, the more normal the distribution of the sample mean is. And that works out to be really convenient for using the normal distribution to do all kinds of tests related to sample statistics like the mean. Yes, sir?
How's that different than
Central
central tendency?
tendency is a type of statistic that you would use to characterize a variable, like mean, median, mode. Central limit theorem says that the more people you have, the closer to normal is the sampling distribution of that statistic. The sampling distribution of the mean, of the median, of the mode, or of the variance for that matter. So even though I've started out this lecture by showing you all kinds of pictures, remember that? Picture time? Picture pages, time to get some crayons and your pencils. No? Remember that?
It sounds like someone's trying to ask a question.
Someone's asking a question? Oh, thank you. I'm still not practiced at like not paying attention to that. Oh, she got booted, it looks like. So, sorry, Tina. Or Trina, damn it. Anywho. I'm getting the names. I'm getting them. So pictures, right? So special thing about binary data, how do you find a mean of a binary variable? The same way as you do for a quantitative variable. The only catch is that there's no variance. Variance is determined by the mean. It's not a separate number. Other variables like 3 categories, Bernoulli, counts with excess zeros, right? These are all different shapes that a variable can have. But if you calculate the mean of these variables, the sampling distribution of that mean approximates normal the more people you have. Even if they look like, the mean came from something that looks like this, even if it came from a box. So we're going to see a lot of stuff that relates to the normal distribution and its friend, the t-distribution, because of that central limit theorem idea. So normal is your new friend. Even if it doesn't describe a given variable, it will describe the sampling distribution of statistics about that variable. All right. I have a few extra slides here that I don't think I'm going to go over this time. I went over it last time and I even bored myself. But it turns out that if you have a variance, you can calculate a standard error of a variance as well. It follows a chi-square distribution instead of a normal one because variance can't go negative. So it can't be symmetric until you move sufficiently off zero. So wrapping this up, the goal of homework 1 is to figure out, number 4. Here, she's back. Okay, yeah, she's having technical difficulties, it looks like. The goal of homework 1 is to give you practice getting into the software, number 1, that's what we're going to focus on for the rest of the time here, and being able to get it to give you this type of information. Frequencies, proportion or percentages, means, standard deviations, variances. That's it. We'll focus on standard error of the mean and tests involving that in the next homework. So, any questions before I wrap up this portion of the program? Okay, so then here is my plan for the rest of the day.